That's all right. I can tell the more lines, the better for me. What's your question?
Okay, hello. You guys hear me in the back? All right, cool. Welcome to Data 8 lecture. I believe this is 15, not 16. Oops, I'll fix that. But today we're going to be talking about sampling. We're going to start by wrapping up our discussion on Monty Hall from yesterday. And then we're going to talk some more about probability and sampling, some two basic components of stats. Okay. So some announcements. So as I discussed yesterday, there will be 4 hours of lecture required for this week. If you have a conflict for the midterm or the final, you have to let me know by tomorrow at 5 p.m. Okay, so send me an email directly if you have a conflict. You must check whether you have a conflict, because otherwise you might not be able to take a final, which would be problematic. Okay. If you feel like you would like more practice doing coding, we're gauging interest in having an additional tutoring session just for coding next week. The form, so we're gauging interest in a form, and the link to that form is on data8.org in the announcements section of our homepage. Okay, so if you're interested, or you would be interested in a tutoring session on just coding and getting up to speed on coding, please fill it out so we can help you out. Homework 4 has been released, and it will be due next Tuesday at midnight. In addition, Project 1 is also due tomorrow. So if you did not know that, now you know. So Project 1 due tomorrow at midnight. Homework 4 released today, due Tuesday at midnight. Finally, I would like to let you know that we have a midterm on Friday, next Friday. Okay. It will be held in class from 10 to 12. And we will probably go to a lab room to take the midterm because this room is kind of dark. But that is TBD. So I'll let you guys know. But do know that the midterm is next Friday. So you should probably start preparing for that as well. Okay. Any questions? Okay, so we plan on releasing practice materials and having like office hour sessions and review sessions for the midterm. So just keep an eye out for that. We'll let you guys know when those are set up as well. Cool. So yesterday, we left off talking about the Monty Hall problem. You're in a game show, okay? And you have 3 doors. You pick a door. Monty Hall opens one of the other doors that has a goat. And you have to decide whether you want to stick with your original door or you want to switch to a new door and get a shiny new car. Okay? So that was the original problem setup. And yesterday, looking at you guys' faces, it looks like you guys are very confused as to why I was writing big walls of code to answer a question like this. I realized that the amount of code that needed to be written to kind of simulate this problem was probably distracting from the actual intent of introducing this exercise. So let me step back for a second and talk about it at a really high level, and then I'm going to go into the code and finish up the simulation. But for today, like, don't worry about understanding the code line by line. Okay, understand the reason why we're doing this in class. Okay, so the reason why we're doing this Monty Hall problem is because it's unintuitive. Okay? It's not exactly clear why it's like 1/3 chances that you're gonna go if you stay, versus 2/3 chance if you switch. It's not exactly clear why it's not half and half. It's not a very intuitive problem to reason out just kind of on its own. So what we wanted to do was use a computer and say, okay, it's computer, if we set up the simulation in such a way, in the correct way, that accurately represents this problem, and just run the simulation a bunch of times, we should see the correct behavior just emerge from the simulation. Okay, so if, for instance, I play 10,000 games, and it turns out that 5,000 of the games I win if I switch, and I lose if I switch, then I can say, oh, switching is not that great after all, because I only have half a chance of winning. On the other hand, I set up my simulation, I run it, and I find out that switching actually gives me the car more often than not switching. Then I can say, it looks like if I just played this game a bunch of times, switching is a better choice. Okay, so that was a reason why we did the whole thing. So now let me go back to the code. And I'm going to fix my screen. OK, here we go. Okay, so if you'll recall, the process that I'm trying to represent in Python is, number 1, put prices behind the doors randomly. Number 2, I pick a door. Number 3, let me make this bigger. All right. Is that more visible? Okay, great. So make that bigger. So I pick a door. Number 3, Monty opens the door. So he reveals one of the doors that has the goats. And then step number 4, we reveal what was behind each door so we can see whether I would have won or not, based on whether I switched or whether I stayed. Okay. So those are kind of my 4 high-level steps. Step number 1, basically what I did was represent the game in a table. Okay. So I'm not going to talk through in detail the steps here. I'm just going to say, OK, step 1, I had this table that has goats and cars. Okay. So let me just run that really quick. Run that. Okay. In this particular game, the car was in the middle, the first goat, and the second goat are on doors 1 and 3. Okay. So this is just randomizing the prizes and giving me a game. Okay. Step 2, picking a door. Well, picking a door is not too bad. All I need to do is choose randomly from the 3 doors available for myself. So from 1, 2, 3, I just pick randomly. In this case, let's say I pick door number, let's run that, 3. So I pick door number 3. Okay. So I pick door number 3. And then Monty opens another door. Okay? So in this case, if I pick door number 3, Monty will have to open door number 1 to show me that there's a goat there. Okay? So whatever door contains a goat, that's the one that he'll open. So in this case, I need to make sure that Monty opens door number 1. I can't just code that Monty opens a door randomly, right? So in this case, I got to choose randomly from the doors, but I can't do that for Monty, because Monty has to actually look behind the doors and figure out which door has the goats. If I just had Monty open doors randomly, then he could open up the door containing the car, which is not representative of the original problem, although it would be nice for me. Okay? So I need to write some code here that has some logic to say, OK, Monty looks behind the doors, figures out which one does not have the car, and opens that one. Okay? So this is just a code that does that. Not super important to go through line by line what it does right now. Just keep the ideas in your mind. Okay, so I'm just representing the problem in code. Okay, so right here I have wrote a function that says, okay, if I open door number 3, let me run that, and it didn't work. Why didn't it work? A game equals setup. Let's take a look. I have to run these 2. Okay, so run that, okay, run that. Okay, so here I just have a function that says, okay, if I give it door number 3, then Monty would open door number 1. So this function just does the process that I described, which is I pick a door, and this function will tell me which door Monty opens. Okay, so just that process in code form. Finally, there is one more door left, and that door is the one that neither me nor Monty opened. And the way to calculate that door is just to say, OK, a little trick here is instead of trying to figure out between 1, 2, and 3 which ones were not taken, I can do 1 plus 2 plus 3 minus the door number that I chose. So minus the door number that I chose, minus the door number that Monty chose. And you can kind of reason out. So take some time on your own and reason out why. This returns to me the remaining door. Okay. So if I pick door 3 and Monty picks door 1, the 3 will be subtracted, and the 1 will be subtracted, and I get back door 2, which is the remaining door. So I run that. Okay, so now I have the entire game represented in Python. Right? So I pick a door randomly, and it has a prize. Monty will then open one of the other doors, and then I have one more door left, which could contain the car or could contain the goat in Python format. Now, what I'm going to do is run simulation. Okay, so I have the game. I'm just going to simulate a game. Okay, so the way I do that is I want to create a new game. Let's call it. So let's say I call a game, and I want to set up a new game. So here's my game table. Okay, so here's a new game. And all I have to do is take a guess. So here is my guess, random.choice among my doors. So here is my guess. So here I pick door 3 in this particular game. Then Monty will open a door. So all I need to do is call the expose function, which is the one that shows me which door Monty chose. Okay, so here is a door that Monty opens. So Monty will open door 2 in this particular game. So let me just show you the game. So here's my game, the one that I generated this time. Monty opened door 2. All right. Then I have the remaining door, which I can just use by calling the remaining function, other game exposed or guess exposed. Okay. And then I can just put all that in a list. So I have here guess, exposed, remaining. If I run that, this says that, Okay, show you the game. This says that in this particular game, I happen to choose door 3, which means that Monty chose door 1, and the remaining door contains the car in door 2. Okay, so I'm just running through the game. If I run it one more time, so let's say I run this. Oops. Okay, whoop. Okay, run that. Run that. So now in this particular game, I chose door 2. Monty then opens door 1, and door 3 contains the car. Okay, so I can run those multiple times. That just simulates different games. All right. So it's not super clear to me. So I don't want just the door numbers. I actually want what was behind the doors. Okay. And to do that, I just need to call my function behind. So I'm just going to call behind game guess, behind game exposed, behind game remaining. And if I do that, now it shows me, OK, in this particular game, run that, I happen to choose the car in my first guess. Monty revealed the first goat. The remaining door contains the second goat. Okay, so the same thing as before. I'm just showing which doors or what was behind each door instead of just showing the door numbers. Okay, so I have here a game, and I want to run this a bunch of times and see how likely it is that I win if I switch versus if I stay. Okay, so if I want to run something a bunch of times, I can use a for loop. Let's say I want to play this game 10,000 times. A range 10,000, right? I can just copy and paste that code in there, and I'll play my game 10,000 times. That's it. However, if I remember last time when I talked about for loops, if I just run this right now, nothing will show up because I'm not saving this result anywhere. So I need to save that result somewhere. I'm going to save it into a table because I have a list of, like, I can make a table with one row for every trial of my game. Okay, so here's my trials table, not trails. If you happen to know what your column labels are of a table in advance, you can create a table in this way, where you create a table and then give it a list of column labels. Okay, so here's I want to say my trial number, guess, exposed, and my remaining. All right. And each time the game runs, I want to add a new row. So trials, and I'll just put in the trial number there. Basically, look through this code in your own time, but basically what I'm doing here is creating a table, running through the game 10,000 times. It'll probably take some time to run. But when I'm done, I get this. Okay? So I have here in my first trial, I got the car in my first guess. Monty opened the door, set first goat. The remaining door had the second goat. Okay, so I do that 10,000 times. I have a bunch of games here. And now I can look at how many games I would have won if I switched versus if I stayed, right? Because if I had stuck with my original door every time, then my winnings would just be in this column right here, right? Because this is my initial guess. This column contains the prize behind my initial guess. If I had just stuck with my initial guess, these are the prizes I would have gotten. Okay. On the other hand, if I had switched to the remaining door that Monty didn't open, then I would have gotten the prizes in this column remaining. Right? So these are my prizes if I stay. These are my prizes if I switch. Let's figure out which ones make me win. Okay. So I can take this trials table and I can group by my guess. And I can see that I get the car about 3,000 times, first goat about 3,000 times, second goat also about 3,000 times. So if I stuck with my original door, it looks like it's about 1/3 chance that I win the car. Okay. On the other hand, if I group by the remaining, and just show you how many of those there are, I see that I win the car about twice as often. And I win each goat about half as often. Okay. And I can show you what those look like by making a bar chart. So let's say I do trials.group guess .bar h guess. Okay. And I see here that right here I have about 3,000 for each one. On the other hand, if I grouped by remaining and bar h the guess or remaining, and I see the car is about twice as often to occur, just looking at these axes here. I can make the axes the same length by doing something like, let me see. p field t.xlim, let's say from 0 to 6,000. But that's my, so I'm changing the axis limits. And here I'm going to do the same thing. So they have the same limits. Okay. So I can see here, it's about twice as likely to get a car as it is to get a goat. So it is indeed better to switch. Okay. So I did not have to work through a bunch of math to figure it out and work through probabilities and like Bayes' rule and all of that stuff. All I did was take my game, write out how the game worked in Python, run the game a bunch of times, and take a look at my results. Okay, so oftentimes you want to use a combination of things to try to figure out what's going on in the world. In this case, we use a computer to simulate. Sometimes we want to use math. And we're going to be talking about how to use math to do that in a second. Are there any questions about this? All right. In that case, let's talk about math. Okay, so today I'm going to be talking about probability. Let me move over. Okay. And there are some basic rules of probability. The rules of probability govern how random events happen. Okay. So the way it works is random events have a chance of happening. If I have a coin and flip it, there's about a 0% chance that my coin will become a dollar bill, as unfortunate as that is. Okay, so the lowest chance that I can have is 0, because some things will just never happen. On the other hand, if I flip my coin, there's about a 100% chance that it will stay a coin. Okay, so we give that a probability of 1 to say this will definitely happen. Most probabilities fall somewhere in between 0 and 1, but 0 and 1 are valid probabilities. Okay, probabilities sum to 1. So what that means is if I flip a coin and the coin lands 50% of the time on heads, it must land the other half the time on tails. Okay? So if some event has some chance, like say 70%, then the chance that it doesn't happen is just 100 minus that chance, which is 30%. Or 1 minus 0.7, which is 0.3. So this is the probability. Okay, so pretty simple. So one nice rule about probability is that if I have some outcomes, and all the outcomes are equally likely, the chance that something happens is just a number of ways to make it happen over the total amount of outcomes. Okay, so let me give you guys a discussion question. So I have here 3 in these cards. I don't know if you can see them, but I have here a blue. Okay, I have here a red. I have here a green. Okay, and what I'm going to do is I'm going to put them behind my back and shuffle them around and not rig the deck. But I'm going to coincidentally pull out green. Okay. Pull out green. This is semi-random. Okay, so pull out green. And then without putting my green back into my hand, I pull out red. Okay. What is the chance of that happening? Talk to your neighbor about it. What's the probability?
The probability of getting green is 1/3, right? But because it's without replacement, so the probability of getting a red is 1/2. So most points together, you got 1/6. You can also think of it as like how many different possibilities are there in that order. There's 6, you got green and red, you got red, you get green and blue. There's 6 of those possibilities. Green and then red is just one of those 6.
Okay, so a couple different ways of approaching this problem. One way is to just list out all the possibilities. So I have here, and just make that lower. Okay, here we go. So I have a couple possibilities for how I draw my cards, right? So I had 3 cards in the beginning. I drew 2 cards without replacement, okay, without putting the original card back in. So my possibilities are I can draw green first and then draw red. I could draw green and then blue. Similarly, I could draw red and then green, red and then blue, blue and then green, and then blue and then red. Okay, so I have these 6 possibilities. All 6 of these outcomes are equally likely because I did not favor any particular one card when I drew, although I kind of did for demonstration. You can pretend that I just drew randomly. So I happened to draw green and red. So all 6 of these outcomes, let's say, are equally likely. In that case, the chance that I draw green and then red is outcome number 1 out of 6, which means that it has probability 1/6. Okay. I also heard some people talking about multiplying probabilities together. So one way I could have done that is by saying, OK, The chance that I draw green on my first draw is I have 1 in 3 chance to draw the green card. Okay, so I have 1 in 3 chance to draw the green card. And after I draw the green card, I have 2 cards left. And I have 1 in 2 chance to draw the red card. So I multiply the probabilities together, and I get 1/6. This is kind of the multiplication rule of probability. And the reason why it works out is because you could think, so here's one way to kind of think about the multiplication rule, okay? So let's suppose that I gave all of you guys a full set of 3 cards, okay? So I gave all of you guys these 3 cards. This illustration was made by a professor from this class named Ani Adhikari. It's pretty nice. So I'm giving all of you guys a set of 3. Then I'm saying, okay, everyone draw 1 card at random. So everyone draws 1 card. And I say, okay, everyone who did not get the green card, walk out of the room. Sorry, you're kicked out of class today. Okay, so these 2/3 of the people will walk out of class and be very sad. These 1/3 of the class will get the green card and be happy and stay in the class. Okay, so about 1/3 of the class will be remaining. So let's say maybe like this third right here are people that got green card. Then I say, okay, of the people that got the green card, draw 1 more card from your hand. And from that group, about 1/2 of you guys will draw the red card, and about 1/2 of you guys will draw the blue card. The one that draw the blue card will be even more sad because you got so close. You got so close. You drew the green card first, but you did not draw the red card second, so you still have to walk out of class. Okay, so the 1/2 of this portion right here will walk out, and I have what's left is 1/6 of my original class because I divided the class into 3, and then I divided that group into 2. So I get 1/6 of my original. So the multiplication rule says if I want to know the probability that A and B both happen, then I want to calculate the probability that A happened and multiply it by the probability that B happens, given that A has happened. Okay? So this given is kind of important, because if I just look at the probability that B happens, in the case that I have 3 cards, the probability of drawing red is 1/3. But if I multiply here 1/3 by 1/3, I don't get the correct results. Okay? The correct result is the chance that I draw green on the first try is 1/3. And then after I draw the green, there are only 2 cards left. Given that I drew a green on the first time, the probability of drawing the red on the second time is 1/2. Okay? Yeah, Kevin?
But if you do a width replacement, wouldn't it just be 1/3 squared then? If you do a width replacement, given that event B is not influenced by event A, like coin tosses.
That's right. So Kevin says, if I had put my green, so on the other hand, if I had taken my green card and put it back in my hand, and then drew another one, now the probability of drawing red is in fact 1/3. And then the multiplication rule says I should multiply 1/3 by 1/3 to get 1/9. Cool. So basically, if you have multiple things that need to happen, the chance that those multiple things happen is always less than or equal to those 2 chances happening individually, because I need multiple things to happen. Okay? Which kind of translates in English to the more conditions I have to satisfy, the less likely I am to satisfy them all. Sad fact of life, but true. Okay? Cool. So let me give you guys another question. What is the probability that I draw 1 red and 1 green? Okay. It's not Python, question mark. Okay. Let me see if I can make this look nice. Darn. Okay, never mind. I tried. Okay, nope. The probability that I draw 1 red and 1 green. This is a slightly different from my previous question, which was the probability that I draw green and then red? This question is asking, I draw 2 cards. What's the probability that of my 2 cards, 1 is red and 1 is green? Talk about that with your neighbor.
In this case, we have a little bit more flexibility because we can have the red one first, then the green one.
Okay. I only hear Kevin talking, so how about the rest of you guys? How about the rest of you guys? Introduce yourself, talk about how you approach this problem. Okay, go for it.
It's not going to be 1/6 plus 1/6. You have either one of those two, this one or that one. So or operator probability translates to a plus sign, so 2/6 or 1/3 chance. So you're not restricted to that. That's why you have a higher probability here.
Okay, so to solve this problem, I can look at again the different possibilities that I have available. Okay, so if I draw two cards out of my hand without replacement, these are all 6 of my possibilities. I can draw the green first and then something else. I can draw the red first and then something else. So these are all 6. The chance that I draw 1 red and 1 green is I can either draw green first and then red, or I can draw red first and then green. Okay, so that probability is the chance of this plus the chance of that, which is 1/6 plus 1/6. Let me do that. 1/6 plus 1/6, which is equal to 1/3. Okay. That illustrates the addition rule of probability, where if I have some event A, in this case drawing 1 red and green card in my 2 draws, and that event can happen in exactly one of 2 ways, the probability of the actual thing happening is the probability of the first way, such as drawing green and then red, plus the probability of the second way, drawing red and then green. Okay. In the multiplication rule, we said if you have multiple conditions to fulfill, the chance is always less than or equal to your original probability. With the addition rule, the answer is always greater than or equal to the chance of each individual way because you have multiple ways things can happen. So you have more options. When you have more options of making something happen, you add them together. If you need multiple conditions to be true for your event to occur, then you use the multiplication rule. Cool. Any questions about that? All right, so let's suppose that I have a coin, okay, and I want to find a probability of getting at least 1 head. How would I find that? Talk to your neighbor. Okay, so 3 tosses, 1 head. Go talk. Go.
If you have 3 tosses, the chance of having at least 1 head, well, we have a possibility of having a head. So the chance of having no heads, that would be all tails. 1/2 to the power of 2. So 3 tosses is just 1 minus 1/2 to the power of 3. At least 1. Okay. So what cannot happen is no heads. That would be 3 tails. If we look at all the possible outcomes of 3 tosses, tails is 1 out of 8.
All right, so the probability of getting at least 1 head in 3 tosses can be thought of and can be calculated more easily by looking at the probability that I get no heads and then doing 1 minus that probability, because those probabilities need to sum to 1. Okay? So in this case, the way I'm going to do it is to find the probability of getting any outcome except 3 tails in a row, because any other outcome of flipping 3 coins in a row will have at least 1 head if I don't flip 3 tails in a row. Okay? So the probability of getting that is 1/2 times 1/2 times 1/2. Getting 3 tails in a row is 1/8. And 1 minus that is 7/8 or 87.5%. It's pretty likely to get heads. Okay? If I were to do 10 tosses instead, the probability of that happening is just 1 minus 1/2 times 1/2 times 1/2 10 times, okay, which is equal to about 99.9%. So this seems a little contrived, but it is, in fact, a question like this is actually, in fact, asked kind of often, because when we're doing sampling in statistics, so if we have some group of people, and we're taking a sample out of that people, we want to know, do I have at least 1 girl in, say, my group of 10 people, okay? Out of like a group of like girls and guys, right? So oftentimes we want to know whether we have at least one or a couple of some amount of subgroup within that group. We can use probability to figure out the chance that happens. Okay, so at least 1 head, and I'm going to take attendance. So please visit bit.ly/@-d8, and I'm going to open up that form and then put up the link back so you can click on it. Okay, so there it is. Open. Excellent. All right, go for it. Everyone in row D, raise your hand. D, excellent. Everyone in row, what's the row having called? Everyone in row G, raise your hand. G, H. Excellent. What about column number 2? Column number 2. My column 2s are asleep. Okay. What about column number, let's do a prime number, column number 7. 7. Column number 7. You know where you are. Count up from 1. All right, column number 7. Okay. So go fill out attendance. Okay, and I'm good on time. All right, so let's move on and talk about sampling. Okay, so sampling is something we do quite often in stats because oftentimes we have a large group of possible options, for example, a large group of people, and we want to take some subset of that group because looking at all, I don't know, like millions of people in the US is a big pain. Okay, so in sampling, we have some group and we're taking out a subgroup. There are multiple ways to take out a subgroup. One way is what's called a deterministic sample, which is a sampling schema that does not involve chance. So that's just saying maybe I'll take everyone with the first name that starts with the letter A. Okay, so deterministic. The other way of taking a sample is what's called a probability sample. The key criteria for taking what's called a probability sample is you have to know beforehand the probability of selecting any single subgroup of people in a population. Okay? And I'm going to show you what that means in a second. You don't need everyone in the group to have an equal chance of being selected, but you need to know those probabilities in order for it to be a probability sample. So let me show you an example using the movies data set that we've looked at a couple of times. So here we go, do that. All right. So I have this table. We looked at it before. It's just all the movies. On the top grossing movies, and we're looking at, okay, so Star Wars: The Force Awakens made a lot of money, and then Avatar and then Titanic. We've looked at this before. Okay, so now let me take a sample out of that data set. You've taken samples so far. We're already taking samples in this class. If I just take, make array, row number 3, and then 5, and then 8, this right here is a sample containing 3 rows. It's a deterministic sample because there's no chance involved. So I just took row number 3 and 5 and 8 from that table. Okay. On the other hand, I can also do something like top.where and then grab the title and see what a title r.containing. And let's say it contains and I get these particular movies. So if I take this, I see Harry Potter and the Deathly Hallows Part 2, Sorcerer's Stone, all of that. Okay, so here's another deterministic sample because I did not involve any chance while selecting these rows. Okay, so I selected them out based on some criteria, but that criteria did not involve chance. Okay, so now let me ask you a question. Let's suppose that I did this. I take np.random.choice, a range 10. So this is taking one at random, one of the numbers between 0 and 9. And I'm going to do top.take, np.arange, start. I have 200 movies in my table and increment by 10. Is this a deterministic sample or a probability sample? Talk about it with your neighbor. I don't hear much talking. Go ahead and talk. First of all, what am I doing here? Why did I do this? Why did I do that? What am I actually doing? And then what kind of sample is it?
0 and 9 for the start, right? And then from 9, we're going to 10 all the way up to 2. Start wherever. That's kind of, that's probability. Because you don't really know right from the beginning what you're going to choose. Right? Here's 1 through 10. Let's start somewhere here. We don't care where, let's start somewhere. I don't choose. The machine chooses.
Okay, so how many of you guys think it's a deterministic sample? Okay, how many of you guys think it's a probability sample? All right, so kind of, it's a little bit hard to say exactly what it is. This, in fact, is a probability sample. And the reason why it's a probability sample is because I can find out the probability of getting any one of my rows, right? So for example, what is the probability that I get row, let's say row number 13. What's the probability of that? It's 1 in 10, right? Because I could choose any of the first starting 10 rows. And then from there, I'll take every 10th row after that. So the chance of getting row number 13 is 1 in 10. The chance of getting row 24 is also 1 in 10. Okay? So I can find the probability of getting each row in my sample. Each row from the population into my sample, it's a probability sample. In this case, this is what's called like a systematic sample, which is a special type of probability sample where I do some randomness in the beginning and then systematically take some subset out. But you should know that it's a probability sample because I can find the probability that each row is in my sample. Okay, that's the important criteria. All right. Oftentimes, we won't go through this trouble of like finding out one of the first 10 and then like kind of incrementing by 10. Sometimes we just want to take 5 rows uniformly at random. Okay, so if I do top.sample 5, what this will do is it'll say, OK, every row in my table is equally likely to appear. I'm just going to take 5 rows out of it. Okay, and by default, table.sample will return to you rows, will sample rows with replacement. So if I sample like say 500 rows, I will get duplicate rows. If I don't want to do with replacement, all I need to do is specify an additional argument, which is with replacement equals false. And that will give me rows without replacement. All right? So that's how to take samples out of a table. We'll be using this a lot in the coming weeks, so just get used to seeing it. This is what's called a uniform random sample. Okay. Cool. So anyone still taking attendance? OK, closing that. All right, so now let's talk about another type of sample, which is referred to as a sample of convenience. This is not something you really want for a sample. You may have heard this term as a kind of derogatory term. Basically, it's kind of a haphazard sample. So in this case, I could sample anyone who walks by. It's not really random, however, and we don't really consider it a probability sample because we cannot figure out ahead of time what the population of this sample is, and I can't figure out ahead of time the chance that I get any particular individual or subgroup within my sample, right? So if I just took movies kind of like haphazardly and just laid them on a table and pulled them out, I can't really figure out the chance that I get any particular movie. And that in fact is problematic because it means that we can't use that sample to infer anything about the population. Okay? So the reason why it's important to know the probability of getting any particular subgroup in your sample is because then you can say, I had, let's say, for example, like these particular movies in my sample, and I got this statistic. Maybe the average movie gross was maybe like 500 million. With the 500 million, because I know that each guy in my sample had 1/10 of a chance to appear, I can use the rules of probability to infer, OK, so in my original population, the chance, like the average gross movie is probably within like 500 in that range. If you take a convenience sample, you can't make that kind of conclusion. Okay, so that's the problem of convenience samples. We'll be doing that inferential thinking in the next coming weeks. So look forward to that. But for now, you just need to know that samples of convenience are not that great. Not a random sample. Okay. So let's talk about distributions. So distributions we've seen before. So for example, we looked at the number of studios. We looked at studios that release movies, and we looked at how many movies each studio released. That is a type of distribution. Another type of distribution is what's called a probability distribution. Okay? Basically, we have a random quantity with various possible values. So for example, a dice that can land on any 6 of its sides. And the probability distribution is looking at all the possible values of that quantity. So for example, which side comes up facing upward on the dice, and looking at the probability of each of those values. That's all there is to it. Okay. In some cases, we can just kind of like reason about that probability and figure it out precisely in a mathematical sense. So, for example, if I take my dice, I take a dice. So my die is, sorry, the singular term is die. So I take a die, my table, and say my faces go from np.a range 1 to 7. And here is my die. It has 6 faces. Okay. I wanted to simulate a roll of the dice, or a roll of the die, I could just do die.sample1 and get back face 2. Okay? So that's one way of rolling the dice in Python. What I can do instead is, well, I know that the probability of getting each of those faces is 1/6, right? So I could take another table. Let me do die.width column chance or probability. And I'm going to say that column contains 1/6. So these are the probabilities of getting each face on my die. And then I can draw a histogram of those. And that doesn't look that great. So let me change the bins to go from, let's say 0.5 to 8, incrementing by 1. And didn't work. That's problematic. Okay. I have prob. And, oh, right. So I want to actually not do a histogram. I want to do a bar chart. Hist. So I want to histogram the faces. And I want to say my bins are A range. Here's A range 7, 1. Okay. And although you can't see it in this histogram, it's supposed to have like a little line dividing each bar here. So I have here 6 bars corresponding to each face, right? And the heights of each bars are the same. So the chance of me getting each face on my die is equally likely. So this is what's called a probability histogram, because it shows me a distribution of probabilities for each particular event. Okay? So all these are equally likely. Unfortunately, it looks like a big rectangular box. But you can imagine with me, OK, here's like face 1, here's face 2, here's face 3. Okay. Cool. So that is a probability histogram. There's what's called an empirical distribution. So let me click past the slide. Right. So an empirical distribution is basically saying, what are the results? What are my distribution of results based on just random chance? So based on, if I roll the dice a bunch of times and looked at how many times each face occurred, I can make a histogram of that. And that histogram is called an empirical distribution because it's based on my observations. Okay. Usually the observations are repetitions of an experiment. So I roll my dice a bunch of times and plot a histogram of that. And the empirical distribution is just what I observe. The proportions of every value that I observe, if I put that in a histogram, I get what's called an empirical distribution. So let me show you what that looks like. An empirical distribution in this case is just taking my die. And if I sample 10 elements from it, I get a bunch of faces. Right? So I have a bunch of rolls on my dice, on my die. And then I can take the histogram again of the faces. But because each face appears a different number of times, I'm going to get a different looking histogram than I did before, right? Because I'm just rolling my dice 10 times and saying, OK, 1 appeared twice, 2 appeared once, 3 appeared twice, 4 appeared twice, right? So I'm going to change that. But you can see here, this is what's called an empirical distribution, because it's empirically measuring the probability distribution. But you look at that and you're like, well, that doesn't really look the same to me. Let's see what happens if I increase my sample size. Okay? So I have my dice, I have my die. I roll it 100 times instead of 10 times. Let's run that and see what happens. So it's looking more flat than before. Right? If I roll it 1,000 times, more flat. Yeah, Kevin?
It's called an empirical distribution. Is the other one the probability distribution?
That's right, that's right. So here I have probability distribution because these are measuring exact probabilities. Here I have the empirical distribution because these are measuring my kind of like simulation, my observations of actually rolling a die 1,000 times and seeing my results. Okay. And the cool thing to know here is that if I keep rolling my die and plotting the histogram, I go from 10,000 to 100,000, I go from 100,000 to 1,000,000. Don't try this at home because you'll be rolling die forever. Okay. You'll notice that my empirical distribution starts to look a lot like my probability distribution, right? And that's because over the long term, if I keep rolling a die, I expect to see all 6 numbers at about an equal rate, right? So when I only had 10 rolls, it doesn't look quite the same because I could just get no 5s by chance. But if I keep rolling, eventually get something that looks very, very similar to my probability distribution. Okay? And this is an important fact about sampling, which is that when I have a large random sample, the law of averages states that if I repeat that a bunch of times, independently and under the same conditions, which means that nothing really changes in between dice rolls, I'm still just rolling a die, then the probability of times an event occurs gets closer and closer to the theoretical probability of the event. Okay? So what that means in English is basically, if I just keep rolling a die, I'm eventually going to see that my empirical distribution looks a lot like my probability distribution. And what that means is every face is going to appear about 1/6 of my rolls. Okay? A really important fact about samples and large samples. Okay? Another way to state that is if I have a large random sample, then the empirical distribution of a uniform random sample matches the distribution of the population with high probability. So it won't always match the probability distribution. So if I roll a die, I could, in theory, get 10,000 ones, right? It could just happen by chance. But with high probability, like it's very, very likely that if I roll a die a bunch of times, the distribution of heads, the distribution of faces is going to look a lot like my original, which is really important because sometimes I can't know what my original probability distribution looks like, right? So let's say I'm trying to look at how likely it is that, let's say Amazon is trying to measure how likely it is that you click on their recommended products. So if you buy a product on Amazon, they'll recommend you stuff, and it's like spookily accurate because it's like, wow, how did you know I was looking at this exact thing, right? So when Amazon's looking at that and trying to figure out how likely you are to click on it, there's a lot of factors that go into how likely you are to click on the item, right? Like the time of day, how rich you're feeling at the moment, whether you feel like, whether the thing is on sale, right? There's so many different factors that go into the probability of you clicking on that link for another item that it's really hard to measure exactly, right? It's really hard to kind of calculate mathematically the probability of you clicking on that thing. So instead, what Amazon can do is do what we've done here and take an empirical distribution, right? They can say, OK, based on my past data of like 1 bazillion people clicking on these things, because I have so many people clicking on it, I can kind of measure empirically the probability that someone clicks on this link or how likely that person is to click on that link. Really important when you can't actually know what the population is, and that's kind of the reason why statistics exists. Okay, that's all I got for today, so I'll see you tomorrow. Hey, Henry, what's up?